But then we came back and we did an in-class exercise, and this in-class exercise for unpaired two-sample test you can find on B courses, and it's just a good example of how you use this non-parametric test in practice. So we did here. This is problem number 21B in chapter 11. We first do some data cleaning, where we make our table tidy, and I use mutate to introduce a variable for the ranks, and I use summarize to find the rank sums, and then using the formula for the expectation invariance of Tx or Ty, you have that T is approximately normal with mean 105 and variance 175, and you can just explicitly calculate. You can explicitly calculate the p-value, right? And this is larger than 0.05, so we would accept the null. You could have done this as a t-test if you were willing to assume that your x's and y's are normal. So let's investigate that a little bit. So I'm first going to check that the variances are the same, which they're not, so I'll have to use that complicated degrees of freedom formula for my t-test, and I just do a box plot in a QQ norm diagram to test to see how normal my data is, which wasn't super normal. But doing a t-test, you find that in fact the p-value is a little bit smaller, so it's more likely that you're going to reject the null using a t-test. Hence, it's a more powerful test than non-parametric, but they're pretty similar. And you could also have done this with using Wilcox.test, and you'll get a similar result. I want to go to doing the paired data. So for paired data, we're looking at the difference of A and B. Call that DI. In particular, the absolute value of DI, we can look at the ranks of that, and the signed rank if we apply a sign if the difference DI is negative. And so the null is going to be that on average these DIs is 0, and as that you can get 2 to the power n different signings for any given ranking that we have here. So for every row you can have a plus or minus, and we have n rows, that's 2 to the power n. So the rank sum for just the positive signs should be about the same as the rank sums for the negative signs. So this W plus shouldn't be too extremely small or extremely large. So our null hypothesis is that the distributions of the DI symmetric are about 0, and W plus is our test statistic, and it shouldn't be too small or too large. It's in this theorem here, it's shown to be approximately normal, and it's quite similar to what we did for the Mann-Whitney test earlier. So we'll do we'll do an in-class exercise with this, but I just want to mention that there's a really good problem that I made optional because I didn't want to make you suffer too much for homework 5, and that's 11.6.26, in which you need to compute the variance of the Wilcoxon test statistic. Now these test statistics, these indicators aren't independent of one another, and you explore that for a concrete example. And so I go and do some standard indicator calculations. So basically, you have a covariant. You have to compute a covariance, and that covariance can be found using the definition of the covariance as expectation of product minus product of expectation. So you can find it out explicitly, and to find the expectation of the product, I don't know how to do that analytically. So if you explore this problem, I recommend you just do a simulation to find that probability, and I even give you the code to do that for this particular baby example that I'm showing you here. So I'll let you explore that on your own. This is worth your while to look at. So then we did an in-class exercise where we looked at paired 2 sample tests, and here I show you explicitly how to compute the signed ranks from before and after, and you can do a t-test on these differences to test that they're 0, but then you assume that these differences are normally distributed, so that's something you should check. But here you go, you can do this and get a p-value of 0.00208, or you can use a Wilcox.test. So Wilcox.test here with paired equals true, and that will give you a p-value that's just a little bit larger. So you have just a little bit less chance of rejecting the null. Not quite as powerful.